Okay, we're going to talk about these topics today. The valence bond theory builds directly on what we have learned about electron configuration of the atoms, and it's very good at predicting what will bond with what in order to complete octets, but it doesn't explain the bond angles that we observe with VSEPR. So the hybrid theory is going to build on that and help us explain the angles that we observe. All right, valence bond theory says that electrons can be shared when atomic orbitals from different atoms overlap. So if you will remember that boron produces an incomplete octet with only 6 valence electrons. Right now it has 3 valence electrons. Right, these are the 3 valence electrons. So it needs 3 more to fill up those spaces. Well, where are they going to go? So here the fluorine atoms can overlap their 2p orbitals with half-filled orbitals of other atoms, but boron only has 1 half-filled orbital. So it would appear as though boron can only accept 1 electron from the fluorine atom in order to make 1 bond. So boron's going to enter an excited state where it can promote an electron, and so now we have 3 orbitals that can accept electrons. So the 3pz, this would be like xyz, xyz. The 2pz orbital here of the 3 different fluorine atoms can now overlap with one of these half-filled orbitals in order to share electrons and create bonds. So the central atom here is boron. It's the one that determines the shape. So we don't need to draw all of the s and p orbitals in the fluorine atoms. So in this structure, 2 of the fluorine atoms are at 90 degrees to one another on the px and py orbitals, and the other is floating around on the s orbital. So the VSEPR theory predicts bond angles of 120 degrees, which is trigonal planar. There's 3 charge clouds, or 3 domains, 3 bonds, no lone pairs. So this gets the bond angle wrong. So here's the problem with valence bond theory. The bond angle is wrong. Valence bond theory says 90 degrees and a random angle for fluorine. VSEPR says 120 degrees. Okay, so the solution is our hybrid orbitals. So when the electron is promoted, the 2s, px, and py orbitals, they kind of morph into this hybrid orbital, and we call it the sp2, and they're identical in shape and size. So your sp2 hybrid orbitals, the size is very exaggerated, and they are called sp2 hybrid orbitals because they're made from an s and 2 p's. So each sp2 is 1 part s, 2 part p's. So you can think of them in terms of the electron domains around the central atom. So there's 3 electron domains, 1s, 1p, 1p, so you have 3 sp2s. And the bond angle is now 120, as VSEPR theory predicts. So if you combine 1s with 2p orbitals, you get 3 identical sp2 hybrid orbitals. So the large lobe of the sp2 orbital is a part that overlaps with the bonding orbital of the terminal atom. As the shared electrons spend 95% of their time in this part of the orbital, the shape is reasonable. Both shared electrons will spend the majority of their time between 2 nuclei and only a short time in the small lobe on the other side of the central atom's nucleus. All right, so here we've got carbon. Only has 2 orbitals with single unpaired electrons. From this, you would think that it can only bond with a maximum of 2 hydrogen atoms. But when carbon enters an excited state, as it's getting ready to bond with the hydrogen atoms, an electron is promoted from the 2s to the 2pz orbital. This gives us 4 bonding sites. These 4 sites morph into our 4 orbitals, our sp hybrid orbitals. So they're all 1 part s and 3 parts p, so they're called sp3 hybrid orbitals. Okay, so the sp3 hybrid orbitals have a tetrahedral geometry. In this case, it's a perfect tetrahedral with bond angles of 109.5, 4 electron domains, 4 bonds, no lone pairs. All of the sp3 hybrid orbitals are exactly the same. Each one is 1 part s, 3 parts p orbital, so they're called sp3. Okay, so 4 electron domains, s, 1 part s, 3 parts p. All right, so valence bond theory flawlessly predicts that 2 hydrogen atoms combine with 1 oxygen atom to produce 1 water molecule. The px has been drawn so that you can see it coming out of the board like straight at you. You can't see the back half of it. So again, there are 3 identical p orbitals here. They only differ in orientation. One's on the x-axis, one's on the y, and one is on the z. So according to the previous slide, we had 2 electrons in px, 1 in py, and 1 in pz before bonding. After bonding, the orbitals are full, but the angle is wrong. So valence bond theory gives us an angle of 90, and VSEPR gives us an angle of 104.5. So here in this picture, the py and the pz orbitals are not in the right shape for sharing a pair of electrons with hydrogen. An orbital is a picture that represents the area where an electron spends 95% of its time. In this picture, at least one of the shared electrons is spending 95% of its time on the other side of the oxygen nucleus from where the hydrogen is sitting. In valence bond theory, shared electrons will move in and out of the lobe of the p orbital that is on the opposite side of the oxygen's nucleus from where the bonding is taking place. If these orbitals didn't change shape during the bonding electrons would be spending half their time in a region where they don't attract the nucleus of the hydrogen atom. So the orbitals must change shape so that the bonding electrons will spend most of their time between the nuclei of the oxygen and the hydrogen. Okay, so since there's 4 electron domains, 4 sp3 hybrid orbitals will be created. 2 of them have lone pairs, and 2 of them have bonds with hydrogen. So in this 3D structure, it's an imperfect tetrahedral geometry. There's 4 sp3 hybrid orbitals because there's 4 electron domains, but they're not identical. The lone pairs will spend more time in a closer proximity to the oxygen atom's nucleus than will the bonding pairs. Okay, someone came in and I forgot where I was. So the 3 sp3 hybrid orbitals containing the low pairs will be smaller than the sp3 hybrid orbitals that are involved in the bond. This will push the charge clouds that bond the hydrogen atoms a little closer together, and so they reduce the bond angle from 109.5 to 104.5. Okay, so here's kind of a little summary, and again, you can think of these as electron domain, because that's what I always think of it first, electron domain. So if you have 2 electron domains, that's your hybridization. If you have 3, that's your hybridization. If you have 4, that's your hybridization. And you can add them up, right? 2, I have 1, 2. For 3, I've got 1, 2, 3. 4, 1 plus those 3 is 4. That's how I always remember it. All right, double bonds. So both of these carbon atoms are considered to be central, and each central with the other carbon and 2 hydrogens is the terminal. So they each have 3 electron domains around them. So each carbon has sp2 hybrid orbitals. So here's your double bond. There is a 2p orbital containing an electron that's left over after the 3 sp2 hybrid orbitals have been formed. Remember that the 3 electron domains result in the sp2 hybridization. So in this case, there's 1 unmorphed p orbital left over on each carbon atom. So the sigma bond results from, the single bond here. This is the sign for sigma. This is the sign for pi. So this is your single bond here, and the bonds with the hydrogen atoms are also called sigma bonds, but the pi bond results from side-to-side attractive forces between the unmorphed p orbitals. So the sigma bond is head-to-head, and then the p bonds are side-to-side. As each carbon has 1 unmorphed p orbital, the attraction between the 2 p orbitals really is considered 1 bond. So all the double bonds result from 1 sigma bond and 1 pi bond. All single bonds are sigma bonds. Atoms can spin on a single bond, they can rotate, but double bonds are rigid. So this double bond here can't flip upside down with one another. They have to spin together as a solid structure. So cis and trans isomers. Isomers are compounds that share the same molecular formula but have different structures. The elements are arranged in different ways. So double bonds can have cis isomers and trans isomers. A double bond can only spin if a lot of heat is added to the system. That's how you get trans fats. So the cis means same. Oh, I have it here, same. So look, they're on the same side of the carbon bond. Trans or opposite. Triple bonds. So each carbon has 2 electron domains, sp hybrids. Each carbon has 2 p orbitals with unpaired electrons left over after the sp hybridization has occurred. So here's your triple bond. Each triple bond is extremely rigid now. And 1 sigma bond, 2 pi bonds for every triple bond. So sigma bonds are stronger. They have shorter. No. Pi bonds are stronger. They have shorter bond lengths and greater bond energies. Okay. This is benzene, and so we have resonance. And electrons are being shared in each pi bond, so the pi bonds can flip-flop back and forth between the adjacent carbon atoms because they're called delocalized. So they can circulate around the structure. So this is like abbreviation. And this is why we use this so often. This is a lot of organic. Okay, bond polarity. So shared electrons spend more time around the most electronegative element in the chemical bond. This gives the electronegative element a slightly negative charge and the less electronegative element a slightly positive charge. All right, so here hydrogen has a electronegativity value of 2.1 and chlorine has electronegativity value of 3. So the difference is 0.9. That makes it polar. Chlorine's more electronegative, so its shared electrons are going to be pulled closer to the nucleus. So the greater electron density around chlorine gives it a slightly negative charge. So remember, this is a partial negative, partial positive, and what we do is we draw a dipole moment. So the positive part we put by the positive atom, and we draw an arrow pointing to where the electrons are going to spend most of their time. Polar and nonpolar molecules. You won't have to make these calculations, but you do need to make qualitative predictions about dipole moments. So in order for a molecule to have a dipole moment, one end of the molecule must have a partial positive charge and the other end must have a partial negative charge. For polar diatomic molecules, the sum of the partial negative charges on the negative end of the molecule is equal to the sum of the partial charges on the positive end of the molecule. Okay, so you know a molecule is polar if, you have to know if a molecule is polar, you must know if the bonds are polar, and you must know the overall shape. So, are the bonds polar? Yes. Do these dipoles cancel out? No, because they don't. There's not another one in the equal and opposite direction. So one end of this linear molecule has a partial negative, the other one has a partial positive. That's what makes it polar. It has a dipole moment. So we know that there are 2 different ends. How about this one? So the bond between the C and the O is polar, but since we have one in the equal and opposite direction, they cancel each other out. So this molecule is not polar. So this would be polar, polar. This one would be nonpolar because they're in equal opposite directions. The bonds between these, the carbon and the chlorine, polar, but they're in equal and opposite directions, so they cancel each other out. Now here, polar bond, right? But the hydrogens are not equal and opposite, right? This chlorine is going to hog the electrons more. So this dipole moment on the chlorine and the carbon is a lot stronger, and it doesn't, these hydrogens aren't able to cancel it out. So this molecule has a dipole. Okay? We have a lone pair. What's in the other direction? Well, it's not equal and opposite, so this is polar. So diatomic molecules contain, those are your H2, N2, O2, F2, Cl2, I2, Br2. They'll have the same shape. They'll either be polar or nonpolar. And this can help chemists design new materials from placing an element from one group with another. All right, try these in class, and we'll check them.